Okay, I'm going to start the lecture now. Sorry about the short delay. I needed to update something on the Mac that I used for streaming. So welcome again to CS264, and this lecture is lecture 11, and we're going to look at object-oriented programming and design. And again, we're going to look at some C# connections there, but mostly this will be a UML lecture and some theory. So we're going to let me just switch there. Okay, we'll mostly be working on this OOP. So we're going to have a peek at the designing class C# hierarchies using Unified Modeling Language. That's the UML, and we'll see how the UML is used to represent software design patterns. So we'll see that a little bit over the 2 hours, you know. So today's lecture will just set the basis, and then we'll look at the patterns a little bit later in some of the lessons. And then for much of the rest of this particular lecture, we will be working on design patterns, and we'll see lots of UML, we'll see lots of C# and see that connection between them. So for now, I just want to take us through some of the basics there. Okay, and you will have seen some of these basics before. I see there's some issue with my camera. I'm not sure. Let me just have a look at the camera controls and see if I can fix this. Settings. Let's see if I can sort that. Settings. Okay, I think that's fixed it a little bit better there. Okay. Anyway, so we're going to look at design patterns from now until the end of the module, and we need to understand how we describe those patterns visually using the UML, and that's what this lecture is about, setting that scene. We get to see code a little bit at the end, and but we won't look at everything today. Okay, so let's start with the Unified Modeling Language. So modeling is the designing of software applications before coding, and it's an essential component of large software projects. Okay, it's absolutely essential for big projects. It's also helpful for medium and small scale projects. And there are different kinds of models. You know, when people say they're going to model something, you know, you can have a formal, say that's a very mathematical model. You might have a visual model, etc. And the UML, for example, is very much a visual paradigm. And we see that as we move through. Okay, and you know some of this already, of course. But what's important, I guess, is to know that a model plays the analogous role in software development that designs and plans playing the constructions of buildings or vehicles or electronic devices, etc. Okay, you can't imagine somebody designing a new phone and the electronics or a radio or, you know, a computer without actually having some schematic or design. So why would you design software without having those as well? So, so using this software model or some design, then engineers that are responsible for a software development project success can be sure that the functionality is completely incorrect. So end user needs are met, the program design supports requirements for scalability, robustness, security, extensibility, and all other characteristics. That's before the implementation in code renders changes difficult and expensive to make. So what it tells us is that, you know, we make a design first, we test the design, and then we code. You know, we don't suddenly start, you know, writing code and not have any design, really. Okay? Well, you can do that, of course, and you probably have been trying that, and I've done it myself for projects, and I certainly haven't used any designs as such for the example programs that we've been using. But then they had very few classes, they were very simple programs, and very straightforward. But as you move up in complexity and they get a little bit more difficult, then you will start having to think about the designs. The surveys, you know, tell us that large software projects have a huge probability of failure. Okay, an absolutely huge probability of failure. Software goes wrong all the time, for lots of reasons, you know. And in fact, it's more likely that a large software application will fail to meet all of the requirements on time and on budget than it will succeed. So modeling now is a key development success tool, really, and that helps it work for us. So you've seen examples, and if we think back to earlier this summer where we had an automated calculation of student grades in leaving certificate, for example, then we had some software that was clearly designed, modeled and designed, and then they built the model, and then they built the software from the code. But actually, when they needed to make some adjustments based on the experiences in other jurisdictions and so forth, you see, people went in and made changes to code. They didn't go back and make changes to the model, and so we ended up getting some errors. Okay, and we ended up getting incorrect marks. So there's a failure in the code because you're working with the code and not actually dealing with the model. Now, perhaps you could have made some changes in the model that would also lead to errors in the code and so forth, but it would have been that one-way process, and it would have been a better process. And we see this happening all the time. Oh, I just go in and hack and make a code, make a change, and then the designs aren't in step with the code, and we have to watch that kind of thing. So really the whole purpose about the UML then is to raise this level of abstraction. And I'm using some references here. It's a great term from this reference called the Unified Modeling Language. Okay, it's down at the bottom here of the screen, and you can click that link and go through to this. Okay, and they tell us that models help design by aiding workers at a higher level of abstraction then. So it can do this by hiding or masking details, bringing out the big picture, or focusing on different aspects of a prototype. So we may be interested in the static structure of our code, or we may be interested in the dynamic structure of our code. And you've seen this before when you've been designing model view controller type applications, where some parts of that are given over towards the interaction, and some are given over towards the static or the model type structures. So the OMG's Unified Modeling Language, it's a trademark, and UML is a registered trademark, helps you specify, visualize, and document models of software systems, including the structure and design, in a way that meets all of these requirements. And that's a quote telling you what it is, And the OMG stands for Object Management Group, and that's an international open membership, not-for-profit technology that, it's a standards consortium, and these are people who are interested in, in building software and having designs and make sure they work for us. So using the UML-based tools, you can always analyze an application's requirements, design a solution that meets them, representing the results using one of or many of UML's 13 standard diagram types, 13 of them. Okay, we're not going to see all 13. Okay. So the current UML 2.0 specification is actually 3.5 and can be found at the link there, omg.org/spec/UML, and it's definitely worth checking. Now, it's a very dense, technical, terse document. So you should really look for books on the UML, and you go to the library website and just type in UML, and you'll find any number of books, including some of the original key texts by Bush, for example. Okay. So what can you model then? Okay, well, you can model anything really with UML, but it defines 13 different kinds of diagrams, as I said earlier. Okay, and these are divided into 6 categories. There's 3 categories. Okay, and there are 6 diagram types, and that represent the static structure, the static application structure. There are 3 different kinds of behavior, and the other 4 represent different aspects of the interactions. Okay, so we can list them and go through them, but you can see them yourself. So you can have structure diagrams, behavior diagrams, interaction diagrams. So we have class diagrams and object diagrams, and we see those later in this lecture today. We have component diagrams, composition structure diagrams, package diagrams, and deployment diagrams. And you can see in many senses, you're moving from this general sense, like the class diagrams, into much more specific sense, like deployment diagrams. So you're looking at something that tells you about how this particular application is deployed, how it works, how it's organized, and what does it look like when you pull all these things together. Then you have behavioral diagrams, and that's a use case diagram. You may have seen these before. They're used by methodologies for requirements gathering. You have activity diagrams. I love these myself. I use these a lot. I use use case diagrams, activity diagrams a lot in my own work, and state machine diagrams, and that tells us a little bit about the internal state and how it might change. And you probably see me talk about those in other modules as well. Interaction diagrams, they're all derived from the more general behavioral diagram, and that includes a sequence diagram, which I really like and use, and we spend a lot of time with this. There's a communications diagram, timing and interactions overview diagram. The core one here, of course, is the interaction sequence diagram. So for small projects, you rarely encounter many of these diagrams, but you should encounter some like a class diagram. You may, in fact, decide to use some object diagrams, and interaction or sequence diagrams are really, really useful, especially if you want to work out how things work, in terms of engagement with users. So if you're building some model view controller type app, you want to understand the sequence and how it works, and you can model this, and you can look at designing the model the static model, classes, objects, and so forth, using the class and object diagrams. And then you can utilize these and with later in an interaction diagram or a sequence diagram to show, well, how do these objects communicate with each other and with the user as you build applications. So here, for example, is an overview of all of the diagrams, really, and how they relate to each other. Okay, and you can see the class one on the left and the interaction ones on the right. And they're, interaction, you can't have an interaction diagram without having some class diagram, because that class will tell us about the objects that we need and the classes that, the classes we need and the objects that are used, or we need, because we create instances of those classes then as objects, and then once we have all those collection of objects, depending on the hierarchy that we have, we can then use them and specify how they might work in a particular scenario or interaction using the interaction diagram. And a lot of the time, these will come from, there will be this sort of interrelationship between the interaction diagram and the use case diagram and so forth as well. Okay. I'd certainly recommend having a look at this link from Visual Paradigm on what is the unified modeling language. Really, really good resource. I mean, it's a free resource as well. I mean, you can look at books, but this is quite a simplified and accessible overview. Lots of diagrams, lots of examples, and it's definitely worthwhile looking. Okay, and of course, Visual Paradigm is a piece of software as well, which we can use, and I'll show you a little bit about later as well. Okay, right. So here we go then, in terms of just a summary of these. So the structure diagrams show the static structure of the system and its parts on the different abstraction and implementation levels and how they're related to each other. The elements in a structure diagram represent the meaningful concepts of a system, and that may include abstract, real-world implementation concepts. As I mentioned earlier, 7 types of those. Okay. The UML behavioral diagrams, they show the dynamic behavior of the objects in the system. And that can be described as a series of changes to the system over time. And when we say changes to the system, we mean changes to the objects or to the databases, whatever the model representation is. So we have a static model that evolves over time, and the evolution is related to the behavioral system of the system. There are 7 types of behavior diagrams, as we saw. Okay. For this module on software design patterns with C#, we're really just interested in the class diagrams, the object diagrams, which are the static structures, and the sequence diagrams, which are the behavioral structures. And again, we won't be as interested in the behavioral as the static, because the patterns tend to be given in terms of designs for static designs using UML. Okay, so let's have a look at the class diagram then. Okay. And that one is central, okay, to the modeling technique. It runs through nearly all object-oriented methods, okay? And the diagram describes the type of objects in the system and the various kinds of static relationships which exist between them, okay? There are 3 principal kinds of relationships in the class diagram, as we've seen already, and they're important. We have associations, we have simple or some dependency ones, we have inheritance, and we have aggregation and composition type ones, okay? So if we go across here, we can see that we have the association that's represented by this line between the 2 classes here. We have some generalization, which relates to inheritance, and we have we don't have any of the aggregation or composition on this particular diagram. So this is just an inheritance diagram mostly, and an association. So we have is-a relationships here, or uses relationships. We don't have the has-a thing happening here really in some respects. So these are this kind of relationships. So we have classes here that are represented. For example, we have a customer class, and we have a corporate customer class and a personal customer class, which both inherit from customer class, and we have a number of augmentations here as well. Okay, so we have name, delivery, phone, credit rating, for example, which are private members here, and we have some additional private members here, and we have a personal customer, which has a different augmentation here, specialization to customer. We have orders, and we have an order line and a product associated with order, and we can see that we have some multiplicity information around these around the associations as well. So a customer can have many orders, and an order will include each order will include 0 or more order lines, and each order line will have more than 0 or many products. Each one will have a product. Okay, so we can read this and we'll see a little bit more about that in a little while. Okay, so here's a really interesting class diagram that it's worthwhile looking at and working through. And this comes from the visual paradigms, what is a class diagram? Okay, so it's a bit more complex, I guess, than some of the ones that we would have seen previously. Okay, now I'm going to work through this because it's worthwhile working through, and generally, and I mean, I have mentioned this on a slide a little bit later, as my feeling is that people look at UML diagrams, but they don't read the UML diagrams. So you get and that's a problem for students who are interested in designing software or designing classes from these. This is a specification. Okay, this diagram over here on the right is an actual specification for the model, the data model for your software. Okay, so it's meaningful, and this model came from somewhere. Somebody had gone through looking at use cases. They'd gone through activity exercises to try to understand, what are we trying to build here, and how does it work? And so how do we have a user engaging with this piece of software? What does the user do, and how does the software respond? And in order to be able to respond, how do we encapsulate in that model the information that we're trying to look at? So if you're looking at Twitter, what does somebody want to do with Twitter, for example? So what are the data? Well, there's the people, and there's the places, and there's the tweets, and all that stuff. And how does it happen, and how does it work? Well, all of this stuff has to be represented somewhere. And then we get to a point as part of a software development or design methodology, and then this class diagram emerges from this. And the bulk of software development process overall, as you know from your software engineering, is about 70% of it goes into the design, and the outputs of that design then are the likes of these models and diagrams. Okay, so they should not be ignored. They need to be used, and they're instructions on how we build something. If I'm building a new piece of electronics, for example, I spend ages working and designing and, looking at the diagram for my electronic components and how they all connect with each other and make it work and power and making sure it's safe and we can test it. And then I get the components and I build it. Okay, so I don't just suddenly start building the stuff. Okay, same thing with this. It's really, really important that we look at that. So we need to learn and be used to reading diagrams and understanding those diagrams. I have a bit of a rant later in the lecture about my experiences of working with these, but we'll get to that a little bit later. I don't want to stress myself out too early in the class. Okay, so let's have a look at the diagram on the right. Okay, and I've taken this particular diagram from, as I said, from the visual paradigms notes on class diagrams. Okay, it's really useful. One of the reasons I did it is because it has this beautiful annotation of all of the various elements here. So for example, we can see the dependency, we can see this is the boundary class, we can see that this is an association, and we can see that this is a note. They've got all these red details telling us. It makes it easy to read this, and it's a great, it's the kind of diagram that I remember them, but you can copy this and put it into, an image, save as an image somewhere, in your notes, and then you can say, well, that's exactly what this means, and that's what this means, so I can understand it. Of course, you need to understand what aggregations, attributes, associations, operations, abstract classes, generalizations, dependencies, and control classes all mean, and some of them you'll have seen already, and some of them you won't have seen, which we'll get to, and I'll describe those in a little while. Okay. But let's look at what we know. The other reason I like this is because you have an example, you have an exercise currently ongoing, which relates to circles which relates to shapes and adding shapes to canvases and generating SVG diagrams from those. And so this particular example as well uses shapes and tells us a little bit about how it would work. So I really like this. It's very, very nice. Okay. So let's say we have a shape, and the shape is an abstract class, okay? And the shape allows us to be able to draw, erase, move, and resize shapes. So the basic idea of this particular exercise, an example, is that you have it's a drawing canvas, it's a drawing application, and it creates a window, which inherits from some frame, and there's it responds to some events, and then there's a whole bunch of tools around here for drawing and working with windows. Okay, but the whole point about that window is this: you can see this open diagram here, this aggregation that tells us this window, essentially, which is our drawing window or our canvas, and you could imagine that this was the canvas that you had in your exercise, would be to contain contains one or many shapes. Okay, and a shape is an abstract class, and shapes may be generalized in order to be able to create circles, rectangles, polygons. And circles here, for example, are composed of points. They have this point, so a point on it doesn't exist without a circle. Now, I know in mathematical sense points can exist, if you like, or you may have points on a canvas, their reference, but they're references rather than actually individual. You might have lines, for example, which are 2 points, which is the distance between 2 points and so forth. But so what's interesting here is we have this generalization, which is the subclassing that's going on. I have a problem with my Mac at the moment with this particular screen. When I move to this resolution and I moved, you can see what happens. It's not behaving correctly, not giving me the full screen. So I can't fix that. So that's why it's jumping occasionally. But if I'm careful, you'll be able to see this. So a circle contains one or many points. Okay, and we have all these methods here as well that we can work with. Okay, so that's what's nice about this. Okay, so I like this because it gives us a design. Now, I didn't ask you for a design in your assignment currently, because I'm trying to get you to focus around C# and understand your C#. But a little bit later, when we look at designing applications and doing work, I'll be asking you to provide designs as well. Okay, and so I need you to give me a design, and I need to see then the software that's associated with that design. And we may organize it, the submissions, in a way, for example, that you submit your designs first, and then you build a piece of software, okay, from that design. I used to teach software engineering many years ago, the core software engineering courses, and really one of the things that we used to see from this was that students would design something and then decide, no, I don't really want to do this UML, it's a waste of time. And then what they do is they just write the code and then use some software and automatically generate the UML from the software afterwards and submit it, okay? And they missed the point, really, and then they didn't get that forward engineering. It was always the reverse engineering that happened. And so the way I dealt with this, really, in my classes, was I broke the groups into teams, and each team then made a design, okay, and the output of that design was the UML, and they had to do this first, and then they would design the code from the UML. But as I was working over a number of years, I found that, well, actually, sometimes there was no connection between the actual code and the UML. Okay, so they didn't actually use the UML in any way to drive the implementation. That became a problem. I tried to figure out how might I fix that. So, because in many respects, with all of the design and all of the talk that went on, and the really good necessary talk that went on as part of the actual design in the team, then the team knowledge also had a sense of, they were all the time thinking about, I want to build and I want to write some code. Okay, I want to write the code. And even though they were doing the UML, they didn't really believe that it was actually useful. It was just some necessary thing that Keating wanted, and it's just annoying, But at least we get some marks for it as an example. But they didn't see the purpose in that. So I tried a couple of things. So then I decided to give no marks for the design. Okay. And then students were putting all this effort in and decided that, well, it's not fair to have no marks for the work that's being done. But so in the end, I gave marks for the designs as well, and then we gave marks for the code, and I gave more marks for the design than I did for the code to try to get that connection that went through. So in the end, I came up with a nice solution. And what happened was that, so we had, say, 10 teams, and then each team would produce a UML design, and then they would hand over their designs to another team, and then that team would then build code from that design. So it meant they had to read the designs in order to be able to build a code, and that worked out quite well. I'm not sure. I'm not saying I'll do that for this particular class, but we don't have team-based work in this particular one. But it's important to realize that you have team projects. You're working in team projects as well. If you're not using the UML, how are you communicating between the designers and the actual developers? Okay, you should be doing this at every opportunity and learning how to do this. Okay, I told you there was lots of rants in this lecture. Okay, but anyway, it's useful. It's useful to know. But so let's read the design. So this tells us how we should build this. Now, of course, this rectangle class, for example, doesn't have a lot of information about this class. You know, we've just left it out. But you know, it's this was made with Visual Paradigm. We could probably click and expose and show that those details here. And just as a reminder, I guess we should see that this particular class here, Circle, has class members, data members, and it has function, members as well here, some methods. Okay, these are the various operations here, and these are the attributes. Okay, and we can see a little bit about the visibility of those as well a little bit later in the lecture. Okay, but it's nice to have this and we work through this. Okay, so you may notice in this particular example that we have, this is just a note. Okay, sorry, this is just a note, which is useful to have, which tells you what's going on, and it's perfectly good to have those kind of things because it might not always be obvious, and where you can help people with your designs, help them. You will see that a couple of these things, these class descriptions here, also have something in angle brackets above them. Okay, so it tells us that this one, for example, window, is an entity class. I'm not sure if you can see the okay, frame is an entity class, event is an entity class, and the shape and all its dependents are entity classes as well. You notice that shape here is an abstract class, and it's not really obvious. Maybe it's not too clear, but if you look at this, it'll tell you that you can see it's italicized, and that's typically how we refer to an abstract class. This is a concrete class, an abstract class, and there are ways to represent using the UML interfaces as well, of course. Okay, so it gives us another level of abstraction in many ways. Okay, but we also have this control class here. We have this control class. Here we have this boundary class, another boundary class, another control class. So for this particular exercise, or this particular model, static model of a drawing application, we see that there are three kinds of classes. Okay, and you may not have thought about the fact that there may be different kinds of classes available. I mean, apart from the abstract class that we would have seen before, and then we can see that in this particular exercise, the abstract class is an entity class, as is the concrete class, dependent on this, or its subclass. Okay? So there are these other classes in here as well, and I guess it would be good to let you know what those are. So so there, you'll see then there's boundary classes, control class. So boundary class, then, and you may have read this already, of course, by looking at it, that's a class that's used to model interaction between the system surroundings and its inner workings. So such interaction involves transforming and translating events, noting changes in the system presentation, such as the interface. Okay. Okay. So these are a boundary class. Okay. Okay. And then a control class, that's a class that's used to model control behavior specific to one or more use cases. Okay, in use cases we use, and we've seen those, and you've seen those in your software engineering. Okay, control classes encapsulate use case specific behavior. So the behavior of a control object is closely related to the realization of a very specific use case. And that's important that we have those. Okay, it's a specific use case. Okay. An entity class, then, that's a class that represents system objects. Okay, so these are like these are just like the classes that you've been working with already. Okay, and they're essentially the business objects, or the logic or your model. Okay, so if you think of those when a model, and I've used that model, and I've used the term model view controller earlier as well, that we've seen this in our web dev. But this particular diagram here is an example of the entity control boundary. Okay. pattern, sorry, okay? So it's very similar to the model view controller pattern, okay? Whereas MVC is used in user interfaces and that interaction for user work, and that's why we use it for developing the web type applications, web interaction, okay? And ECB is a general pattern for structuring backends. So, you know, there's all this interrelation. So everything you've learned and understanding with the model view controller in terms of the design pattern will apply here as well. So this notion of an entity, control, and boundary gives us a way of looking at how we might structure an application, okay, and how we separate out the kinds of classes that some will work with the entity, some will work with the control, and some will work with the boundaries, okay? So it's nice to have that, okay? So boundary, for example, could be a REST API, control could encapsulate the logic of the design, what's happening here, and then entity itself is the model, okay? So, you know, this ECB pattern, it's not one of the fundamental Gang of Four design patterns that we look at, but, you know, there are lots of patterns beyond those, but these are, it's almost like a deployment type pattern. It works for us, okay? Guys, if you've got questions or anything, you just ask them in the chat. I'm happy to answer them as I go along, okay? Okay, here then, let's look at this. So remember I talked to you about reading the diagram. So shape is an abstract class, okay? It's shown in italics. Shape is a superclass, and circle, rectangle, and polygon are derived from shape. A circle is a shape, okay? Shape is part of a window, okay? You can see that here because we have this aggregation. It's part of, okay? It's an aggregation relationship, and shape can exist without window. So we can have shapes, and they can exist without the window, okay? And you might say, well, how's that case? Well, because we might design a shape, we might copy a shape, we might save a shape somewhere in memory, and then we might save it into a database, or we might save it as part of a design. We might draw and undo and then redo. So we may want to actually play with shapes, okay? But we put them or add them to a window. So that's why it, you know, it isn't composed of shapes. It's just an aggregation, okay? So point is a part of the circle, okay? And that's a composition relationship. So in other words, points don't exist without circles. Okay. You can think about that in some way and how you might look at it and whether that makes sense or not. You know, you say, well, you know, how do we? So in other words, what happens is that inside the circle we create points. I'm not sure that's a good idea. I'm not so sure this is a good design. Later in the lecture series, we'll talk about designs, good designs and bad designs. But for now, I'm just happy for you to be designing, okay, at all. And hopefully you won't get into any bad habits. You know, that would be something we might have to change. But we'll see from there. We see that window is dependent on event. Okay? This is this dependency relationship here. Okay? Event is not dependent on window, okay? The attributes of the circle here, radius and center, okay, that's radius and center. And again, this is an entity class. The method names are area, circum, set center, and set radius. Now we know from some of the examples and some of the C# that we've been doing already that, you know, there are good ways and bad ways to do this. I mean, and there are alternative ways. Okay, and they're not all good and not all bad. Okay, what's good and bad is how you set up the accessor and mutator methods within this. But for me, I like to use C# properties. If I'm using C#, I'll use properties. If I'm using Java, I'll use the getter, etc. Whatever. If I'm you know, using JavaScript, again, it'll be a different way again. You know, but that's fine. But nothing in here tells me about how I need to generate code from this, okay? This design, this could work, and we could be thinking about building a JavaScript application here. We could be building a Java app, you know, or a Windows app. It could run on a phone. It could be running in a web environment. Nothing tells us about that. So this diagram is just about the static model here, essentially, of the classes and how they interact. And that's why we have all the other diagrams. That's why we have about 13 of these diagrams. It tells us a little bit about all that stuff, you know. So it's really useful there to have the different kinds of diagrams. Okay, this is very much, you know, it tells us about how we build this, but it doesn't tell us how we build the software. It just tells us how we build the data structures that are used in this. Okay, You'll notice, as I mentioned before, that the actual attributes and method names of these rectangles and polygons have been hidden. Okay, and sometimes you do this for clarity. Okay, but they will have a similar structure to the one you have for circles here. Okay. Okay, so notice, okay, so you might say to yourself, what's not, what's missing? Okay, sometimes it's important to look and say, well, what's there? Can I read what's missing? So there's no role information here. We don't have window contains shape, for example, along this line here. So sometimes, we see contains a little arrow, I've seen that to you before. The road provides this directional information of our purpose of the association. So we were trying to say the way it's organized, we're reading from left to right here. So that gives us a little bit of information about that, And we also look at where the diamond is and what the aggregation is. Also, in terms of navigability, we can see that the arrows indicate whether, given one instance of participating relation, it's possible to determine the instance of the other class that are related to it. So we don't have any navigability here issues around this as well. And you can look this up if you want to see more about this. Okay. So in object-oriented design, there's a notation for visibility and for attributes, that's the data members, and operations, which are the methods. There are 4 types of visibility: public, protected, private, and package. So it's not surprising that you will have these in C# and Java. Okay, because we need to have these. We're trying to get from the model to the actual code, and we use the plus, minus, hash, and tilde symbols before an attribute and before the operations in order to denote the visibility of that attribute and the operation. And you can see all of this. We just see pluses and minuses, and we know protection and here we have we tend to have this protected symbols. And tilde symbols when we've got class hierarchies. Okay. So the diagram, as we said, also shows the multiplicity details, how the objects can take part in the relationship. So we can see the star here, and we can see the star here. Okay, but we have lots of them. We can have 1 to 0, 0 to 1, 0 to start, 0 to many, 1 to many, 6, whatever. It just doesn't matter. There's all types of different aggregation types here. Okay. So that's class diagrams. I mean, there's lots more we could say. I could spend all my time talking about these, but I haven't done. So we have the object diagrams. Now, we don't have much to say about the object diagrams. But at the top here, we have a class diagram. We have a user and has an attachment. Okay, and so a user perhaps has uploaded an attachment. So we might have some role here describing this association if we wanted to say user uploads attachment. Okay, and we have the information here. We don't have any methods shown here. We just have the data members. The user has an ID and a name, and the attachment is an ID, a string, and an extension, and so forth. And a user can upload more, 0 or many attachments. And it's an example from this. What is the class diagram actually as well? Document. So the object diagram really then is some kind of graph and we use the word graph and diagram interchangeably. Okay, it shows the instances. Okay, including the objects and the values associated with the various class. So here's a diagram, class diagram, and here's the object diagram below it or beneath it. Okay, so we see the instance of the user here. Okay, and we see the instance of the attachment. Okay, so really it just shows a snapshot of the detailed state of the system at any point in time. Okay, and it might be useful to have these if you're going to do some testing, for example. And you might want to be able to look and say, well, assuming we have this particular setup, how does the software evolve or behave over time? Okay, so the class diagram represents the abstract model, and that consists of the classes and the relationships, and the object diagram represents an instance at some particular moment, in time that's concrete. Okay, and they have they're limited kind of use. Okay, and they're mostly to show examples of the data. Okay, so I'm just going to go back up, fix this because it's worthwhile here. Yeah, they've limited use. It's mostly to show examples of data structures. As we've said already, this particular diagram, we have a user and attachment. The user can upload multiple attachments, so the two classes are connected with this association on the attachment side, and it just shows this particular example then shows the instances. Okay, that's the instance specification. So we have 2 instance specifications, this one A1 and this one A2. So you'll see that we have the object's name here, and we have the object class following. It's very straightforward. Okay. So the next diagram, and we won't have time to do it in any good detail like we do with classes, but you could work through it in the same way, and you could also go and have a look at this particular textbook, or just these notes on what is the sequence diagram. You can click through to the link and get there. But as we saw, the class diagram provides us information about the static structure of the system or the nature of the system, and it tells us nothing about how the classes and object behave in the deployment. Okay, nothing at all. And sometimes you don't get to see this, so this is really useful. So the sequence diagram helps us with this, tells us about the objects that are participating in the interaction, and then how they interact and the messages and so forth. And it's really useful. And this is actually, I suppose, the class diagrams help us with generate the static structure of our code and how we get classes from that, and the interaction diagrams gives us the program flow or the algorithms that we'll be using. Okay, and so that's the way to test. So performing some activity, and again, these all come from an activity ultimately. Okay, so as a person wants to book a hotel room, for example, this is an example of how you might do it. So you can specify the algorithm, if you like, as part of the sequence. So it tells us how and the sequence, and also just tells us about the objects or members that are participating in that sequence. Okay, so they're time focused. Okay, very much they're time focused, and they show the order of the interaction. Okay, visually, using this vertical axis of the diagram, and you can see that happening here. There's the vertical axis here, and it shows the messages that are passed between the various objects that are participating in this. Now, they're not classes participating in this particular one. Of course, you could have static classes that are participating in some way too. They might be providing information that's necessary as well. Okay. So, for example, we have the message, which is called. Okay, so here we have this window, and it's the user interface, and it starts by sending a message to make a reservation to this a chain, okay, which is an instance of a hotel chain, and then we choose a hotel, okay, and we choose a specific hotel in this particular chain. So we want to make a reservation in a hotel. We first of all contact the chain, then we contact this chain, contacts the hotel. Then we have some iteration that exists here, okay, and we can iterate over this loop, and we can have some messages that we can send back to ourselves, okay. Or alternatively, we could do this, and what happens is that as we progress through this, we get the information then passed back along the timeline until we ultimately stop. Okay, and this is a bit more complex, but it's incomplete. But it's worthwhile having a look and seeing how these things work. Okay, again, this is about the sequence of events, that algorithm that works, and you can do this in advance of your software as well. So it tells us how it works, and these, remember, will relate to the use cases, okay, and the activity. Okay, so very often we would start with a use case. We will work through the use case, and we could look at the participants in the use case. Person wants to take money from an ATM or something like this. There'd be a person who would have details, they would have a card. They want to book a hotel, all this kind of thing. We think and we figure out what all the classes are, and we extract that from the use cases and build a class diagram. Then we go back and we look at the class at the use case scenario, and then we will. And sometimes we work with user stories as well. We figure from those. But use cases are different from user stories, because use cases tells us about how systems respond to user interaction. User stories tell us that background from the perspective of the user in many respects, what they want to achieve, and so forth. So when we have these use cases, then it details some of the steps. So you'll see then how we can get the sequence diagrams from the use cases as well. So it's kind of nice to have those. Okay. Anyway, we'll see those a little bit later. Okay. Remember, it's an interaction diagram that details how operations are carried out. In other words, what messages are sent back and forth. The messages are method calls. Okay. Sequence diagrams are organized according to time. As time progresses, you move down the page, okay? And the objects involved in the operation are listed from left to right according to when they take part in the message sequence, okay? So you can see how these interaction diagrams are dynamic, okay? These aren't dynamic in themselves, but they demonstrate dynamism, okay? And it shows you how they collaborate, okay? And we'll see a little bit more of that again later, okay? That's nice. Okay, so I always think about, like, when you say I'm designing with UML, well, are you really designing with UML? So my teaching and learning experience, as I mentioned already, has been that students don't always appreciate the value of modeling and design in UML. That's probably why I'm laboring it here. The diagrams that accompany reports, for example, I see lots of final year project reports. They're kind of some kind of summary artifact that's generated afterwards and it's replicated in the developed code. Okay, there's a disconnect between the methodology that they would have, for example, Scrum, and the designs in the UML. There's no connection between how they designed and the outputs of that design and then how they developed. And often then going the other way, the developed code actually bears no more resemblance or semblance to the static and dynamic designs. Okay, so we need to look at correcting that. The UML models then actually have to be meaningful. Okay, you have to understand why you need them, why you actually use them in your development. Okay, in large projects you get a design and you're expected to realize it in code. As I said, I try to replicate that in some of my other modules that I taught. In small projects you have the opportunity to use all of the models and learn about them to get some practice for later. You can imagine, again, if an electronic engineer worked without designs, you know, just it's unthinkable. So why would computer science students just write code without designing it? You know, I don't understand it. Okay, so you really need to take time to read and figure out how you might test the design as well, specified in the UML. That's another story. So we want to test the design rather than test the code. Okay, and then, you know, that's a really good exercise as well. We don't have time to do this, but, you know, in software engineering, you know, it's time to do that. Right, so you really need to design with UML, please. So, okay, so if you want to get started with all this, you may have used some design tools in your software engineering models. You could have learned, you could be learning about design methodologies and processes. You might know about waterfall, feature-driven, agile, Scrum, extreme programming, lean. And again, UML can be used in conjunction with all or any of these processes or any other process yet to be invented. Okay, typically in large projects, UML development tools are used to create designs. Like, you don't draw them by hand, or you don't use a graphic software. You know, the tools that you get tend to be aligned with specific development methodologies. Okay, so if you have a methodology that I'm using Scrum or I'm using Agile, then you'll buy a tool and use a tool that supports that. Okay. The other thing is that the tools tend to be designed in a way to support large projects, not always available, you know, for proper full usage within small scale projects, and they're costly, but there are lots of free and inexpensive ones available. So I've given you a link. I suppose in some respects I don't want to recommend. There are lots of good ones, and you've probably seen Star UML and some of the others that you would have in here. But if you click this link here, that'll give you a searching point for some of the tools, and it gives you a nice list of all the tools that could be used. Personally, I've used and downloaded the Visual Paradigm. Okay, and you click through the link, you can get that at website. There's an online one. It has a community edition that supports my requirements, so I like that as well. The other thing as well, it also runs on macOS, and I'm a macOS person, so it's useful for me. I think I would have had more options if I was working with Windows, and probably fewer options if I was working with Linux. Okay, but it's important to realize, of course, that the Visual Paradigm and these kinds of tools, they are modeling tools. They're not drawing tools. Okay, so really important. I also use Plant UML for modeling and drawing UML diagrams. You may have seen them in some of my lessons. You can also design with UML with Visual Studio. This is the 2019 Windows version. I can't do this on macOS, so that's why I'm not using Visual Studio at all. I do say that I've got a bit of a demo here. I think if I click through to Visual Paradigm, there's an online Visual Paradigm. You can work and you can click through and see some of the, let's go down to, these are all the different kinds of diagrams that you might have, but I'm interested in a class diagram, so it should be here somewhere. Where's our class? Here we are, look, class diagram. Click on class diagram. Here's some example class diagrams that they've generated already. Here's one for a car. Let's have a look at this. And you can make these and add these yourself. I mean, it's not going to be difficult to do this, but it's worthwhile doing. I've downloaded the community edition. It didn't cost anything to have it. And here I have my design. And you can just add and look at all these designs, you know, and you can do all sorts of extra things that you want to be able to have here, you know. You can have, you can work with all of these. You can add, you can change, you can work and create new designs, change it in some way. You could say it's a car model. car, you could turn this into an abstract, for example, extra class support. And so you can work with these designs with Visual Paradigm online. I'll probably do a little bit of that, and I'll show you a couple of examples in some of the lessons. I've also downloaded Visual Paradigm, and I have it running here, so you know it works fine. Again in my Mac, which is really useful for me. Okay, let's do this. As I said, I'd also use Plant UML for drawing UML diagrams. I don't know. Yeah, so it's pretty good. Okay. So it's straightforward. We've got about 5 minutes left, I guess. So it's because I started a little bit late. So it's straightforward to manually generate code. Okay, so if you look at Visual Studio, if you have Visual Studio and if you look at Visual Paradigm, they give you options. The paid versions give you options to dynamically generate code. Okay, and that's really useful. But for us, we might want to be able to look and say, we can generate code fairly straightforwardly from the UML diagram. So there's this connection. So as the diagrams become more complex, however, it becomes more difficult to generate code, and that's why we have code generators, especially for hundreds of objects and classes, hundreds of classes. So that's why we use tools like Visual Paradigm or Star UML and others to design models and then automatically generate the code. And it's a good thing to do. Okay, it gets us up and running very, very quickly. I tend to use manual examples, and I'll do this in some of the lessons where I'm going to give some of the James W. Cooper's 2002 book on C# design patterns tutorial. And you know, this is an example of some of the code that he would have had and some of the examples. So here's a person string. Here's a person class. This is like person class without any of the accessibility issues there, and then here they are, the accessibility, and then here's the code that corresponds to that, the C# code, and you can see the private string name corresponds to private name string, and it's fairly straightforward in order to be able to do this, and it's not hard to do. As I said, you might say, well, it's easy, why would I do this? Very clear. With easy classes and small amounts of classes, it's easy, but for large scale projects, you do need to do this. Okay, so here, for example, is an example of an abstract class. Person, and then we have an employee that's generated from as a subclass of the person class, and we have our diagram here. Now, you know, this is 2002 when James Cooper was writing this book, but you know, this is how we would have represented the abstract class here. I mean, actually, it's perfectly okay to have your lines, but what's important, I guess, is that the title is italicized here. That's person. I'll be doing this for you and showing you this a little bit later in an example, but I will be I'll be using Plant UML, or I'll be using Visual Paradigm. But you know, it's a good book. It's nice. Chapter 6 gives a description on UML. So if you can get a hold of this and look at chapter 6, it'll show you and work you through with some C# examples as well. What about the UML model code generation? That's going the other way, because as I did say, you know, I was a bit dismissive about it, but there are circumstances when it's useful. For example, if you want to generate a model from your code to compare visually with your design, to say, well, how's my code comparing with the design? You can actually do that and then do the comparisons. And there are many ways to do it. You can use VS Code and some Plant UML extensions. I can have a demo to do this. I'm not sure it's going to work in this particular one because it relies on GraphViz, but I had it earlier. It didn't seem to work terribly well for me, but let's see if I can switch to VS Code now. So I installed here's an example class that I used earlier for circles and shapes and so forth. And what I did is I generated some UML. So this was my C code. Okay, it was you know, an example you've seen previously. So and if I look at the command palette, and I install this module or package C# to Plant UML. So I ran this, and literally that was me running it. Okay, and it generated some UML for me. So I was able to look at the UML, and I was able to get the UML, and so this produced Plant UML. So that was really nice. And this allows me to generate a diagram from this. So I was able to install and work that. It was really nice. And then I could run the command palette and got a preview of the current diagram, which may not work because I haven't installed GraphViz on my computer. I had it running in the background before, like, oh, it did, yeah, excellent. So it started working, okay? So this shows me that I had this circle class here. Okay, and it was embedded in the program, and we can see various dependencies and so forth here as well. So yeah, I was able to dynamically generate this code from my I see here as well, and that was really useful. Okay, and I like this. Okay, and then it should generate the diagram. So somewhere for us as well. Yeah, I can generate. Oh, that was the output that I had generated from my program. Okay, and I should be able to save a copy of this as well. Okay, and it's fairly straightforward to do that. I can do that. Save this diagram, and I like it. So we should, in principle, be able to take the examples from Cooper's book here, put them into a C# file, save them with VS Code, and then automatically generate the UML diagrams from this for us. And again, it's a useful thing to do, if you're using it for the purposes of comparing with designs. Okay, so we learned about implementing C# class hierarchies here today. And we learned a bit about the UML class diagrams, small bit about sequence diagrams. We looked about. We get to a small pattern. We saw a pattern that could be designed with the UML in mind, and we're going to see a lot more of these as we work through the second half of this course. But I just hope that you have a sense of how it's important for us, to be able to distinguish between the various kinds of algorithms and patterns and designs, and we use the UML for that. And you need to become comfortable with this, and then you need to get used to using it and actually using it as a way to help drive your designs as well. But most of the patterns that we'll be seeing as we work through the rest of the lectures will be will be specified using the UML, so please get to know it. You may have seen some of it before, but you may have kind of brushed it off in passing and never given it the attention it really needs. It's a super skill to have, and definitely worthwhile learning. So thanks for coming to the lecture today, and I'll see you soon. Okay, thanks again. Bye-bye.